You do not always need Elasticsearch to search documents. DuckDB can give you local full-text search directly from Python. You'll learn how the pieces fit into a workflow that indexes documents locally and searches them without a separate service. I'm Professor Pi, teaching AI foundations with simple Python. Imagine you have a folder of notes, a small FAQ, or a few thousand support tickets. You want fast, ranked search from your analysis environment without running a remote search cluster. DuckDB Full-Text Search brings search into your Python process and your notebook. It removes the friction of deploying and maintaining a separate search server, and it keeps data local for privacy and speed. At a high level, DuckDB builds an index inside the same database file you already use for analytics. You create a table with document text, instruct DuckDB to build an FTS index, and then ask for ranked matches. The ranking here is BM25 style, which balances term frequency and document length, so short, precise documents are not unfairly penalized. For most local tools, the result is instant relevance and simple integration with Python workflows. We will build a tiny local search demo. You will see how to enable FTS, load documents, create an index, run stricter queries, and wrap it into a reusable function. The goal is a small, practical search API you can call from a notebook or a script. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need to enable DuckDB's FTS extension, so the database knows how to do ranked search. This snippet opens a local DuckDB connection and loads full-text search support. The pain we are removing is the search server itself. No cluster, no daemon, no HTTP endpoint, just a Python process with duckdb.connect. Con execute install FTS and con execute load FTS make DuckDB ready for its FTS SQL features, while the tiny select one gives us a clear sanity check. The visible output shows the connection is alive before we put documents into it. Now that the database can do search, we need some documents to search across. This example turns a few readable Python tuples into a real DuckDB table. Small, local search still needs a stable shape, an ID to identify each document, plus searchable text fields like title and body. Con.execute many writes the toy collection in one call, which mirrors the same pattern you would use after reading files from a folder. The visible output confirms how many documents DuckDB has stored, so the next step has a concrete corpus to index. With documents present, we can build the FTS index and try a first ranked query to see results order. This snippet creates the actual DuckDB full-text index and asks for the best match. Without the index, we only have rows. After pragma create FTS index, DuckDB creates the FTS main docs match BM25 search macro for this table. The query computes a score, filters out non-matches, and orders the remaining rows so the strongest match rises to the top. The visible output shows which document wins for ranking, proving we now have ranked local search instead of plain substring filtering. A raw ranked list is good, but sometimes we want fewer loose hits and more precise results. This snippet tightens the query so casual matches do not crowd the results. By default, a multi-word search can match documents that contain only some of the words, which is useful for recall, but can feel noisy in a small document browser. Passing conjunctive x1 into FTS main docs.match BM25 requires every query term to be present before a row counts. Increasing strictness usually reduces the number of hits. Relaxing it usually brings back more candidates. The visible output shows how many documents satisfy both terms, which is a practical relevance control. Once the query works interactively, you want a tiny function you can call from code or a UI widget. This code wraps the DuckDB FTS query into a tiny, reusable local search function. The function takes query and limit, passes them through con.execute, and returns only the document titles, so the caller gets a clean result list. Keeping the SQL inside search gives you a baseline you can later connect to a CLI, notebook widget, or small app without changing the index. The visible output shows a complete search call returning a real document result, which is the smallest useful local document search demo. To map this toy demo into a real project, replace the hard-coded tuples with rows loaded from your document source. Read Markdown files or CSVs into Python. Write them into the same DuckDB table and rebuild the index. For a medium-sized notebook project, this keeps everything local and reproducible. Quick recap: DuckDB FTS runs in process, so you get ranked BM25 style results without running a separate search cluster. It's a great fit when you want private, simple search inside a Python workflow. And one caveat: if you need very large-scale or heavy concurrent querying, a dedicated search system will still be the better choice. A sensible next step is to tune the ranking by adjusting BM25 parameters when you create the FTS index, specifically the BM25 K1 and B settings to better match your document lengths and user expectations. If Python tools for AI Foundations help you, subscribe and watch the AI Foundations videos.